तेरा
वो बंद कर डालना।
Start. Good morning to one and all. I am Nilesh S. Mahajan, Assistant Professor, Department of Electrical Engineering. Welcome you to the second day of STTP AICT sponsored short-term training program on digitally controlled power converters for industrial and renewable application phase 3 under AQIS scheme. It's my privilege to introduce you the today's speaker, Dr. Ragavan K, Associate Professor, Department of Electrical Engineering, IIT Ganndhinagar. Dr. Raghavan did his BTech in Electrical and Electronics Engineering in Pondicherry Engineering College, Pondicherry. He did his ME in Power Electronics and Drives in College of Engineering, Gindi, Chennai. He received his PhD degree from Department of Electrical Engineering, Indian Institute of Science, Bangalore. After the completion of PhD, uh, he was working in GE India Technology Center Private Limited, Bangalore, as a research IP professional and research engineer. He joined the Indian Institute of Technology, Ganndhinagar, in May 2009. His research interests are conditioning monitoring of transformer, design of rotating electrical machines, and drives for electrical vehicle applications. So without taking your much time, I would like to request Dr. Raghavan sir to please start his session.
Good morning to all of you.
Good morning, sir.
Thanks for a nice introduction.
Thank you.
Is my voice audible to all?
Okay. Yes, sir.
Sir, whether participants are allowed to show their faces or there is some technical issue?
Sir, we are not allowing them to turn on the video because it takes the internet data. So
Okay.
that may be a problem during the session.
Okay. Okay. Whether am I allowed to turn and keep the
Yes,
camera?
sir, sure. Yes, sir.
Okay. Okay. So at any stage, if the things are not clear, you please interrupt there itself so that I'll be very comfortable rather than pushing the question and answer session towards the end. So it will be good if you can pose the question. You can avoid sending chat message to me because once I start doing the presentation, I'll not be able to see the chat window. So you please turn on your microphone that time and then you ask the question.
Yes, sir. Yes, sir.
All right. It's about grid connected wind energy conversion system. This is the overview of presentation. All right. You can just go through this. So The wind energy penetration to the actual power generation is being listed out, and this has been taken from a paper published in the year 2008. Okay, so obviously the penetration will be more now. So when you are talking about wind energy, basically the wind power is converted into mechanical power, and then mechanical power is converted into electrical power. So initially we will talk about the conversion from wind power to mechanical power. So the x-axis is tip speed ratio and the y-axis is power coefficient. How much power can get converted? So this is about the theoretically you get around close to 60% when the optimum ratio is chosen. What is this optimum ratio? It is a ratio of tip speed divided by the wind speed. Wind speed is usually expressed in meter per second. So the typical value of wind speed is around 10 meter per second, 12 meter per second. Now, what is the speed experienced by the tip of the turbine blade? Okay, so that is called V subscript T. Tip, the speed experienced by the tip of the turbine blade. So when the wind speed is varying, we are trying to adjust the turbine blade so that the ratio will be around 5. So that is the optimum tip speed ratio. So that time the corresponding power conversion will be the best. Okay. Now, what the next graph is the power versus wind speed. You can consider it as a electrical power. Now you see when the wind speed is from 5 meter per second and up to 15 meter per second, there is a linear change. As the wind speed is increasing, therefore the power is also increasing. After 15 meter per second, so the power that is obtained is constant, whatever may be the wind speed, up to 25 meter per second. Beyond 25 meter per second, there is no power. Now I want to ask you the question. Up to 15 meter per second, what we are doing is we are adjusting the turbine blade so that the tip speed ratio is optimum value, and we are getting the power which is a linearly changing as that of the wind speed. That is clear. From 15 meter per second to 25 meter per second, why is the power constant? Why it is not increasing in the same way as we are observing between 5 meter per second and 15 meter per second? Any answer? Hello? Sir, Paresh sir, am I allowed to pose question?
Yes, sir. Yes, sir.
Yeah, okay. So I am permitted to pose question. So I'm posing the question, and it will be good if somebody responds to this. 5 meter per second to 15 meter per second, there is a linear change. Between 15 and 25 meter per second is constant. Why it is not increasing? Because since we are getting more wind power, so mechanical power and hence electrical power also should increase, right? Whereas we are seeing electrical power is 1 per unit. Anji? Hello? No, otherwise it will be very boring actually, because speaking to the screen is really boring. So it will be good if somebody says something so that no, I feel like, okay, there are some audience. Okay, otherwise it looks like I'm talking alone. Hello? Then I have to call the name, I think, right? Should I repeat the question?
Yes, sir. Yes, sir.
Yeah. From 5 meter per second to 15 meter per second, the power is electrical power that we get out of this wind energy conversion system is increasing. As the wind speed increases, therefore power is also increasing. That power, instead of expressing like megawatt, we are expressing in terms of per unit. Up to 15 meter per second, it is fine. But 15 meter per second to 25 meter per second, the power is constant. Since the wind power is, since Vayu Bhagavan is giving more and more power, why we are not able to convert that into electrical power? So this figure has been taken from the book that is mentioned in the bottom of the slide. So why between 15 and 25 meter per second, the power is constant? Why the power is not increasing? Okay, I will give you a hint. The wind energy conversion system consists of turbine. Then we have the gear system. Then we have the generator. Okay. So now you please think about this. Why we are not able to get more power when the wind speed, in spite of the wind speed being very high in number, right? So why we are not able to get that? Why we are not able to make use of that? Why it is 1 per unit? Kripaji? Okay, I think she left.
No, sir, I'm here.
Okay, any answer from your end?
The mechanical forces?
No. You are giving the complete answer, or you are giving hint and you are asking me to develop the hint. Between 15 and 25 meter per second, why we are not able to convert the wind power to electrical power? I gave the hint as the wind energy conversion system as turbine, gear system, and generator. It's there in this. Okay, anybody else?
The extraction could be low, sir.
No, they go 5 meter per second to 15 meter per second. It is as the wind speed increases, power is also increasing. Beyond 15, why it is not increasing? So there are two things. Is it not increasing, or we don't want it to increase? Now you please choose one of these options. I will give the option. Anji?
We don't want to increase.
Great. We don't want to increase. Why we don't want to increase? Why we are not? Why we were happy with Vayu Bhagavan up to 15 meter per second, but after 15 meter per second, we are not happy. I mean, no, enough. Chodo, enough like that. Why? We can still go. No, we can keep on going up, right? Anji.
So it's because of rating of the machine we have reached.
You are great. So we have the generator. We have already put a generator. That generator is for this much megawatt, mega volt ampere, whatever may be that. So we have already put the generator, thinking that 15 meter per second is the highest wind speed we will get in that terrain. But all of a sudden, if we are getting 20 meter per second, we cannot change the generator again. Do you follow? Right. So corresponding to 15 meter per second, that system will give 10 MVA output. Now the speed goes to 17 meter per second. So obviously it has to give more. So, but suppose if you are allowing it to give more, then what will happen? The current in all the windings will cross the rated value. So finally the windings will be burnt. So we don't want, although the wind power is more, we don't want, the only reason is we cannot convert because we have already installed the generator. So then why we are not installing the generator everywhere some 20 MVA, okay, so that we can make use of that. So then what happens? Most of the time, if the wind speed is around 7 meter per second, 8 meter per second, then the machine will always be underloaded. All of you know, if any electrical apparatus, if it is underloaded, instead of operating at full capacity, if it is underloaded, the efficiency will be low. So we have to study that terrain. What is the typical wind speed? So most of the time, this is the average value of the speed. So accordingly, the generator capacity is decided. So that generator will deliver one per unit, whatever is the capacity of the generator corresponding to that particular speed. All right, is that okay? Say yes.
Yes, sir.
Okay. Okay, so that is what is written, protecting the generator. Increase in turbine speed is prevented to protect the generator from overloading. So when the wind speed is more, then the blades will be adjusted such that the conversion will correspond, whatever conversion you could get for corresponding to 15 meter per second, the similar conversion only you will get. So the the increase in wind speed is not going to get converted into corresponding electrical power. Okay. Now, beyond 25, Anji,
Can I ask one question?
yeah, you can ask.
Sir, here let us say if we make use of increased wind power, and okay, we will not supply that to generator, but after let us say some indicator is there, and if we could divert the power to some energy storage element, and uh, so whether such incorporation is possible.
Kripaji, this is your innovation. Yes, it is correct. You are getting mechanical power out of the turbine. Instead of giving it to that particular generator, you divert that mechanical power to some other generator. Okay. So yes, that is always possible. So basically, to the same turbine, you can connect two generators. That's what you are saying. Correct? No. So actually, it is innovation. You can, but unfortunately, you have leaked your idea, so you cannot think about doing patent. So to the same turbine shaft, you connect two generators. So one generator is always converting this mechanical power to electrical power. Another generator will come into picture whenever the wind power is more. Whenever the wind power is more than 15 meter per second, let's say it's between 15 and 20, so that excess mechanical power will be diverted to the another generator. Correct? No?
Yes, sir. And
But
sir,
you, Ji.
I mean, is it just connected with the rating of the machine, or maybe more wind velocity, so higher stresses, and it may not be permissible for the wind turbine kind of thing is also.
You are talking for which range? 15 meter per second to 25 meter per second?
No, sir. Actually, I don't have much idea about speed and corresponding mechanical forces, but just
No,
this.
no, no. Let's convert this graph into statements. Are you referring to 15 to 25 meter per second? That range you are saying? Right, so that range is connected with the generator. We don't want a generator from overloading. Okay, so that is connected with the, we have already installed the machine which is meant for this much rating, this much power. So now excess mechanical power, if it comes, it cannot convert into generated electrical power because the windings will be carrying more current. So we don't want excess mechanical power. So then the turbine blades will get adjusted such that the additional mechanical power is not available. Only whatever conversion you had done for 15 meter per up to 15 meter per second, that conversion only you are getting. Now the next question is, beyond 25 meter per second, the electrical power coming out of this wind energy conversion system as per the graph is zero. Why is so? Now the wind power is huge. Actually, the wind speed is huge, 25 meter per second. Okay, so but the electrical power as per the graph shown is zero. Hey, we have designed both turbine and generator. We have installed. Now the wind speed is more than 25 meter per second, but the electrical power is zero. Hanji? No, it will be good if you speak, because some chat message you are sending, every time I will not be able to check that. Maybe somebody has already given the answer for the question which I am asking now. Okay. Anji, oh, by mistake I clicked also. Don't look at the screen now. Without looking at the screen, please tell the answer. Without looking at the screen, please tell the answer. By mistake I clicked it.
Power extraction, sir.
Oh, you are not looking at the screen. You are honest person. Okay. Now you please look at the screen and then tell me.
I already told this, sir.
When did you tell? When did you tell?
Before, sir.
No.
Before you asked the first question, I was telling this.
Okay. That's what I said. You are answering to a question which I did not ask. All right. Right.
Yes,
So
sir.
that, yeah. So this is applicable only after 25 meter per second. Okay. So up to 15 meter per second, the conversion we are doing. Beyond 15 meter per second, we are actually ceiling. We are having a ceiling because of the generator capacity, limited capacity, right? So then beyond 25 meter per second, the entire wind energy conversion system is such that itself is stopped, because there will be a structural damage. You also said, and Kripaji also said, okay. So this is to the second point, protecting the generator is electrical side, you can say, and turbine you can say about the mechanical integrity of the overall system we want to take care. Okay, can I go to next slide?
Yes.
So I went. Yeah. There is a title, why high speed motor even for low speed application. The typical speed of the wind turbine, can anybody say that what is the typical speed of the wind turbine? Any guess? What is the speed in revolutions per minute? Can anybody say what may be the typical speed of wind turbine? Anji?
200 RPM, sir.
200 RPM is slightly on the higher side. You can still reduce it. Okay. You can visualize 200 RPM is on the higher side. Okay. So maybe 100 RPM. All right. So now let's say 100 RPM. To this 100 RPM, are we connecting 100 RPM generator? So although the title is motor, just that is to explain on something else. Now to explain this, then I will go to motor. Do you think to the shaft of the turbine, which is typically rotating at 100 RPM, do you think the generator which is designed for 100 RPM is connected? Is the question clear?
Yes,
Is the
sir.
question clear?
Yes,
Clear. Okay.
No, sir.
Question is not clear? Okay.
Question is clear, answer is no.
What answer is no? Question is, I asked whether the question is clear. Okay, clear. Thanks. Okay, now to touch that, I will take a topic, take a example, elevator. Okay, the lift. What is the typical speed of the lift? Meter per second, can you say? 1 meter per second? Okay. Now, this is a very low speed movement, right? So what is the motor connected? Anybody knows what is the motor connected?
Induction motor.
Great. Now tell me, is it a high speed motor or a low speed motor? 1 meter per second is a very low speed.
Yes.
What motor is connected? Low speed motor or high speed motor?
High.
High speed motor, because that is the title of this slide. No, so don't think too much. So although it is a low speed, why you are introducing high speed? Therefore, there has to be some interface between the low speed load and the high speed motor. What is that interface? We can't directly connect, no.
Yes.
Gear system will be there. Okay. Now, if you directly, you want to go at a very low speed, why don't you connect directly to the shaft of a low speed motor so that the gear system can be eliminated? Gear
Torque,
system is not, Anji,
torque requirement would be very high.
torque requirement would be very high. Great. Um, so to meet high torque requirement, what you are doing? You are putting a gear system like that.
No, to meet low torque requirement.
No, but this load requires high torque. This load is because we are all standing inside the lift room. So
Torque,
the torque
torque,
requirement is high. Anji,
torque versus load characteristics, sir. If you follow that characteristics curve, so we can easily eliminate the motor sizing. That is the main
okay,
key.
okay. To reduce the size of the motor, correct? For a power level with low speed, suppose if you have decided low speed, if you are directly connecting, then for that much power requirement, torque has to be high, right? If the torque has to be high, if you look at the relation between the torque and the dimensions of the motor, we can write as torque is proportional to diameter square multiplied by length, right? So power we have fixed, how much power we require to elevate this room with so many people from this level to another level. We have decided the power, this much power is needed. Now power is equal to torque multiplied by speed. Now we will have to decide where you have to give the burden, because basically this power is a team effort between torque and speed. Suppose if you outsource this job to the speed, I mean, if the speed is high, then the torque is low, then torque is connected with the volume of the rotor. So therefore, since you require for the same power level, you require lower torque value. Therefore, to meet that, the size of the machine comes down. So for a higher value of torque, machine size would be dash. Very simple question I am asking, which I have already explained. Also, you also have explained. What you will fill up in this blank? A person who has not answered so far, that person should try. For higher value of torque, machine size would be dash. Which one you will put there? Anji? Okay, I will answer. Machine size would be more. All right. As a result, power density of the motor becomes, in this case, higher value of torque, machine size would be more, then the power density of the motor becomes power density in the sense in the space available. You are introducing a motor, you are replacing a motor. So for the same space, if that machine is capable of giving high power, then it's called high power density. Okay, so now what will be the answer for this? As a result, power density of the motor becomes dash. Low. Great. Hence, for improving power density or energy density, whatever may be that, you prefer high speed motor. The same way, now come back to this generation, right? The turbine we have, and we are not directly connecting to the shaft of the generator, right? And the generator is high speed. If the generator, if you're going for the same speed as that of the turbine, 20 RPM, 50 RPM, or 100 RPM, in that range, so then it's a low speed generator, then the generator will be very big. Okay, so we want to cut down the cost. So for that, no, you have to introduce one more system. This gear system is something equivalent to a transformer. Okay, so like how this low voltage generator gets converted into high voltage with the help of transformer, so that the transmission losses can be reduced. Similarly here, the moment the torque requirement comes down, so then the current in the windings also will come down. So therefore the losses also will come down. So by introducing the gear system, you are improving the efficiency of the system. The gear loss also will lead to some losses, the transmission losses, but compared to that, the overall electrical losses come down. So therefore, with the gear system, the overall wind energy conversion system becomes efficient. So typically, it's a geared drive. So wherever you go, it is gear drive, but there are some locations where windmills will have no gear system. Okay, so that we will see, that is called direct drive system. Otherwise, generally it is a gear drive system. You can see the advantage and disadvantage, right? When you don't have gear, so basically you are eliminating one mechanical system, therefore the maintenance comes down. And gear also results in some losses, transmission losses, mechanical transmission losses. So that losses get eliminated. So whenever you reduce the number of subcomponents, the reliability of the overall system improves and also efficiency. But here also we can say that disadvantage is more because of the generator size. So that is the main, and economy, all that you can add. Okay. Now, which generator we have to choose, right? So some little bit of introduction about the generators. All of you know this, that I know, but just for completeness, I have introduced here. Synchronous generator, whenever we talk about generation, immediately we think of synchronous generator, right? So this synchronous generator, either it could be electromagnet or permanent magnet in the rotor. So whenever you talk about high power rating generator, the field is sitting in the rotor. Okay, so if we talk about low power generator, something like less than 5 kVA, so then you can have other way also, like the field could be on the stator side also. But typically, if you see any book, they take the field in the rotor, considering the high power rating of the synchronous generator. So the statement, if you are connecting this generator to the grid, and grid is maintained at certain frequency, therefore the shaft of this generator should be driven at the same speed, so that you will get the frequency as that of the grid. So in that case, you will have to see what is the typical speed of the turbine, but we are not directly connecting, we are putting a gear system. So after the gear, that ratio, then what is the speed that the shaft of the generator will see. So then the number of poles are decided accordingly, so that you get the frequency from that generator which matches with the grid requirement. Now another generator is asynchronous generator. It is also known as induction generator. We don't have a separate source for providing the field. Then who is providing the field? Working principle of motor I will tell initially. If a current carrying conductor is kept in a magnetic field, it experiences force. Working principle of generator, if a conductor is moved in a magnetic field, then EMF is induced in the conductor. So whether it is a motor or a generator, field is needed, magnetic field. Whenever I say field, I am referring to magnetic field. Whether it is a motor or generator, magnetic field is needed. In induction machine, if we want that machine to act as a generator, we provide mechanical power to the rotor, and rotor is being rotated, and there is no separate source for providing the field, right? So then who provides the field? So if we simply rotate the rotor, whether we will get electrical power in the stator side?
No, sir.
Okay. Hello, then you expand, please.
Sir, some capacitor bank are used, or sometime grid connection is done to get the reactive power requirement.
Yes, yes. So we have to establish the magnetic field. That magnetic field is established by connecting the stator windings to the grid. So the grid, from the grid, it will take care of the required amount of reactive power. Okay. Now the same question, whatever frequency that comes out of this generator, that should be connected to the that should be synchronized with the grid frequency. Similar to the synchronous machine, can you tell me what should be the rotor speed? So I have put a dash also. Please fill up the blank. Options are also given. Sometimes option may not be there. That part, that also you have to take care. What should be the speed of the rotor, so that you will get electrical power at certain frequency which matches with the grid frequency? What should be there in that blank?
So it will be more than the synchronous speed.
Okay. Any other answer? Hello? Any other answer? So I'll write one statement. Okay. Is it visible?
Yes, sir. Yes, sir.
SM stands for synchronous motor. Synchronous motor produces stable torque only at synchronous speed. Is it legible? No?
Sir.
Yeah. Now, induction motor is also known as asynchronous motor. I want you to make analogous statement for induction motor, which is also known as asynchronous motor. I want you to make analogous statement. We are doing some English test now. English test and logical reasoning. Synchronous motor produces stable torque only at synchronous speed. Now you have to comment about asynchronous motor. I mean induction motor. Hello, tell me. Bala is very good at that English aptitude. So I request Bala to respond.
Sir, I'm thinking,
Or
sir.
anybody else? Oh, you are thinking. Okay. Sometimes he's very humble also. So he doesn't want to show off to people the way I'm showing off. Isn't it? Pare sir? Okay.
Yes, sir.
A synchronous motor produces stable torque only at asynchronous.
बस ये क्या होता है? Asynchronous motor produces stable torque only at asynchronous speed. This is too much actually. I said make analogous statement. You are simply saying asynchronous motor produces stable torque only at asynchronous speed.
It will
That
not produce stable torque at synchronous speed.
what? It
My
doesn't produce.
I will take back my statements.
No, no, no. You are saying it doesn't produce. You are saying, Anji. What did you say?
No, sir, let me think.
Okay, okay. Others? What about others? Shyamji, you want to say? Shyamji, are you there or left?
Sir, a synchronous motor makes various torque at various speeds. I mean, it is, we cannot correlate it.
So you are finding fault with my question, it seems. Okay, I said you make analogous statement. Now you are saying that this question is a useless question and we cannot correlate. Is it possible? Yes, Pawarji, yes. So what you are saying, I'm asking you to make an analogous statement. Okay. Analogous statement means most of the things will get reflected in that. Yes. I will start. Somebody please help me. I'll start. Anji.
Sir,
Ah,
actually, it will not produce stable torque at synchronous speed.
great. But it's actually negative statement. Can you make affirmative statement? Because we are having this motor. Then I will go to a generator later. We are having a motor which has to produce some torque. So can you make affirmative statement? So I'll start. Maybe you can help me. A synchronous motor produces
Stable torque.
stable torque. Great. Mm.
Other,
At at any speed.
other than synchronous speed.
Great. At any speed other than synchronous speed. Right. So from this, whether this statement is acceptable to everyone? Okay, silence. So it is acceptable. Okay. So therefore, the speed of the motor, induction motor, can be less than ns or it can be greater than ns. Okay. Only thing is the speed of the rotor is not equal to ns. Is this true, false? So whatever I put arrow mark, true or false, you have to bubble one of these. Hello. No, somebody is talking, but voice is not audible to me. I've kept full volume in my system, but even then not audible. Is this true or false?
So it's true.
True. Whether we have to do polling, whether everybody agrees that this is true. So the speed of the motor, induction motor, can be greater than the speed of the magnetic field. So where ns stands for the speed of the magnetic field, the speed at which the magnetic field is traveling, revolving, rotating, whatever may be that. Whether everybody agrees the speed of the induction motor can be more than the speed of the magnetic field motor.
So then it will become induction generator. If
Ah,
speed is greater than ns, so first
madam,
option is only correct.
madam. Okay, so you are saying it is false. Okay, so I am talking about a motor. Why motor? Because almost all of us are very familiar with the motor compared to generator. So I want to finish motor first. So whatever statements I have made so far, whatever is written here, all are connected with motor only. Okay, so for motor, is this true or not? For motor only, no generator. Generator I will come just after this. For motor only, whether this is true or false. And one hint I will give you. Whenever I give the first option, most of the time the first option is the correct option. Most of the time, sometimes no, there may be little deviation. Okay, I have given hint also. Bala?
Yes, sir.
No, I'm not taking attendance. I'm
True, sir.
asking the answer, true or false?
True, sir.
True. Okay. Because you are trusting me, I think. Mostly the first option is correct option. That way, no?
That way also, sir.
Oh, some people don't trust me. That's okay. Okay, what about others? So far, I've got two different responses from two people, true as well as false. Anyone else?
True, sir.
2. Great. But if you look at the book, it's generally written the induction motor speed is less than the speed of the magnetic field. So that we will see, right? Now I will come to this. Now you tell me for a generator, the speed of the rotor in generator. The speed is taken care by the turbine. Turbine after that gear system. If you want to generate, now I have explained some answer we have got. I think majority is agreeing with the true. The speed of the motor can either be below synchronous speed or it could be above. So that is what, but I have not explained so far. I will explain that later. Then what is your guess on generator? Is it something similar or it is totally different? You rotate the rotor either at less than the synchronous speed or more than the synchronous speed. In both the situations you can generate as long as you provide the mechanical power and somebody is establishing the reactive power. Is the question clear? Forget about answer. I'm talking about the question. Is the question clear? Induction generator. Since we have written for motor, so analogous thing I'm writing, N should not be equal to Ns. What N should not be equal to Ns? There is a speed. At certain speed, magnetic field is traveling, revolving in the air gap. You should ensure that you are not providing mechanical power at the same speed. So then it is not going to generate. If the speed is other than that, then it's going to generate. This is the statement. I'm not writing. Is this true or false?
False, sir.
Any justification? Shyamji, you agreed. Here you have bubbled true, right? Here you have encircled true, correct? No?
Yes, sir.
Okay. But whereas here you are saying false. Any reason? There is no match, right? Because now also it's called as asynchronous generator. Earlier, before this line, I said is asynchronous motor. The same machine, now it is a asynchronous generator. Okay. Why? Because somebody is providing mechanical power and reactive power is also being established. Therefore, it is generating. And it is not synchronous generator, it is asynchronous generator. If you are saying the speed of the rotor should not be equal to the speed of the magnetic field in case of motoring mode, why the same is not true in case of generating mode? There is a contradiction, no? Shyamji, you are getting my
Sir,
question?
it is because of
Okay.
the flux generated, sir.
No. Reactive power. See, don't worry about the magnetic field. Don't worry about the flux. Flux is taken care by somebody else. Right now, we are getting mechanical power. Mechanical power means it is only dash power. Please fill up the blank. Mechanical power means it's only dash power. Please fill up the blank. Rachana ji,
Yes, sir.
mechanical power means only dash power. Before this, Shyamji was telling about magnetic flux. So then immediately I switched over to mechanical power means it's only dash power. So can you put an appropriate word here?
So that is useful power that will be converted into the power.
Great. But there is a very popular terminology used in electrical engineering to refer it to that power.
Active power.
Great. So we are getting active power from this mechanical system. That power we want to convert into electrical power. Okay. So only for electrical we differentiate active and reactive, because reactive means it's oscillating back and forth between source and load, whereas in all other domains it's just active power. So therefore we are converting, and the flux requirement is taken care by the some other source. It could be grid, or it could be a battery connected with inverter. So that is how, I'm not just talking about capacitor. Capacitor will help if there is some field is existing, residual field. But if the residual field is not there, then connecting capacitor is not going to help. You will have to generate that reactive power. Okay, so for that you can go for some battery and inverter. Now, where are we? If you have agreed to the statement, although some of you did not agree, but most of you had agreed, asynchronous motor means it can rotate at any speed other than synchronous speed. So why I cannot extend the same statement to generator? Whether you want some time, or should I proceed further? Say something. Okay, it looks you are all tired, right? Hello.
No, sir. Give some hints or
No, sir.
others.
Okay, so what I have to do? Should I proceed further, or you want some time, like 2-3 minutes you want, and you are thinking?
I'm thinking, sir.
Okay, thinking. Okay, fine. Now, logically, forget about the statements that you have read in books. Forget about it. Logically, what option you will choose here? You assume that you know nothing about generator, induction generator specifically. Logically, whatever explanation I had given for asynchronous motor, I want to extend the same thing to asynchronous generator. Somebody is providing mechanical power. Let's talk about a simple case. Simple case in the sense it's a four-pole machine. Four-pole machine and 50 hertz is supply. Okay, grid. It's connected with the grid. Okay, so you have the machine and you have the grid lines. Okay, so basically this is wind energy conversion system generator, induction machine actually. Now the rotor is rotated by the turbine together with the gear system. So that means what? Mechanical power, it comes in this direction. Now I will put two arrow mark here, and you will have to tell me what does this two arrow mark represent. So still your domain, I think, is this one.
Sir, could you please repeat once? I mean the question.
Two arrow mark I'm putting for the stator windings which is connected to the grid. Okay, you tell me what does this two arrow mark represent. Whereas here this side from turbine gear I'm putting a PM, stands for mechanical power. Now you tell me about this two arrow mark that is shown with the generator, between generator and grid lines.
The reactive power is taken from the grid.
Okay, and
And
active power is given.
Yeah.
Great, great. Whether everybody agrees to this?
Yes, sir.
Great. Now, typically, if you look at the book, mechanical power should be given at a speed. So 4-pole 50 hertz means you can say that the traveling magnetic field is at 1500 RPM, correct? Okay. So we expect this speed should be more than that. So let me say it is 1510 RPM. All right. All right.
Yes, sir.
Okay. Due to some reason, the speed drops to 1490 RPM. What will happen? That is the question. So once you know, you get some idea, then it's done, right? For some reason, so 1510 RPM, for some reason it has dropped to 140/90. After putting gear system, we have gone for a maximum gear ratio. After that, we are getting 1490 RPM. So what will happen now? But the traveling magnetic field is going at 1500 RPM. Now, for some reason, the mechanical power you are getting at 1490 RPM. 1490 and 1510 RPM. Do you think there is much difference between the speed? Okay, I should change the question. Do you think that there would be much change in the power? Two options I will give you. No, yes.
No, sir.
No, right? Because 1510 RPM, that much power, and 1490 little bit. So it's a huge power. Okay. If you can generate at 1510 RPM, that much power is available. So now what will happen? So when I ask this question, most of the students, they immediately say, this machine will act as a motor. Correct? Most of the students,
Yes.
I'm not saying your answer. Most of the students say that this machine will act as a motor. It will act as a motor means to which it will give power. See, whenever something is generated, whether it is an electrical generator or mechanical electrical motor, when it provides some power, somebody should be there to receive it. Actually, now turbine is giving huge mechanical power. Now, why there is no logic? Why this machine has to act as a motor? Because huge power is given. Traveling magnetic field is there. So logically, there is a way to generate, because what is our requirement? Our requirement is if conductor is moved in a magnetic field, then EMF has to be generated. Now you have this magnetic field established by, taken care by the grid, and we have the mechanical power. And the only thing is the speed has dropped a little bit. Okay, so this is what we are going to discuss. There is a one popular machine. Maybe I'll start writing. I want you to tell me what is that. Okay? What is this? It's not a good drawing. Don't look at that beauty of the drawing. But can you tell me what it is? Okay, not able to understand. Okay, to the rotor, I'm connecting 3 resistors. And we have been discussing, yes.
Slip ring induction machine.
Yeah, so you can say phase bound induction machine. Okay, so what is the need we are going for this machine? Now I will draw the characteristics of the machine. So you take torque on y-axis, speed on x-axis. So the characteristics of induction motor will be like this. Okay, so just I will finish induction motor first, then I'll go for generator. Okay, now I'm not connecting to the speed axis because we know that it doesn't produce a stable torque at synchronous speed, but at any speed other than synchronous speed, right? So by adding this resistance, what happens? You will get another characteristic. So this is something like resistance 2 and this is resistance 1, where R2 is greater than R1. Maybe R1 you can assume that no resistance is connected. So basically you are, for the same torque requirement, you are able to operate at two different speeds. So basically you can do the speed control by having this resistors connected with this rotor windings. So this phase bound induction machine have a similar set of stator windings, 3 windings. Both stator windings and rotor windings are designed for the same number of poles. Now, I'm talking about motor, I'll come to that later, for generator later. So now, what is this? You have PG, where PG is the air gap power. So if you look at this equivalent circuit will have a resistance and reactance in the rotor side. So then that resistance, what is the value of this resistance? Let me say, I'm just writing for the rotor side. So let me say it is a reflected current, I2 prime. So what is this resistance value? Hello.
R2 prime by S.
R2 prime by S, correct? No?
Yes, sir.
Okay. Now the active power that is transferred via the air gap, that I'm writing PG, which is equal to 3 times, because it is a per phase equivalent circuit, I2 prime square R2 prime by S. Okay. Now this SPG, yes, I'm taking this side. So what is this called? What is this called?
Slip power.
Slip multiplied by power is slip power. Great. Anything else? Hello. I'll start writing P C.
Copper loss. Rotor
Great.
copper loss.
Great. Even if the rotor conductors, even if the rotor is made up of aluminum also, we have to call it as a copper loss. Okay. So rather than copper loss, maybe better is ohmic loss, but I will call it as a copper loss just for convenience. Okay. So copper loss is equal to S times PG. Now here in the characteristics, you have some slip S1 and some slip S2, where S2 is greater than S1. By increasing resistance, you are able to alter the slip of the motor from S1 to S2, or you are able to reduce the speed of the motor from some N1 to N2. The slip increases, but the speed decreases. Okay. So for that, what you are doing, you are okay. So what you are doing that time, you are dissipating some power in the rotor circuit. Basically, you are increasing the copper loss so that the operating point of the machine gets changed from point A to point B. Okay. Now, I want you to do some change here. What is that change? What is the change? So let's say, so can you tell me what is this? What is this value? S times PG, agreed? Which is equal to copper loss. Forget about loss in the rotor conductors. So basically the main power is this one. So is this okay? Hello?
Yes, sir.
Okay. Now what I am doing, I am just enclosing this 3 resistors, whatever you have the resistors, I'm just enclosing. And I want to do something there. Can anybody guess what I want to do there? SPG is coming here. But I want to do, I am closing this, that 3 resistors, whatever we have there, I am closing this. Can anybody tell me about some innovation? Unfortunately, you cannot pattern this. Some power comes because we have decided to change the operating point from one speed to another speed. For that, we want to do something there. Can anybody guess? Bala? To change the operating point, we have to transfer SPG to this circuit. So it is going there, right? But can you make this system as more efficient now through some way?
So we can store the power
Great.
by
Store.
converting through.
Yeah. So what you can do, you take this, remove this resistors, okay, put power electronic converter, and then convert that power, take it and feed it to the grid. Do you follow what I'm saying?
Yes, sir.
Okay. So whether everybody is able to follow this? Say something. Shyamji?
Yeah.
Okay. So what I am asking, you put converter. So these 3 lines are coming from rotor. These 3 lines are coming from rotor. So now you just remove all those resistors and put a converter here. Then again you put one more converter. Okay, so 3 lines are coming. So then you have the grid lines. Okay, tell me what is the frequency of the current rotor frequency? What is the frequency here? Frequency of currents in the rotor side. And tell me that this, you know this, all this.
S times a stator frequency.
Okay, S times, okay. So typically it is 2 hertz, something like that. Now this one is AC to DC and this side is DC to AC. All right. So this frequency has to be 50 hertz so that you can match with the grid. And also you will include transformer so as to match with the voltage, because this voltage is very low value. Whatever comes from um, this rotor side, the frequency as well as the voltage both will be low. So to match with the grid requirement, you will also include transformer, which I'm not showing here. Now, what is this called? So can you give one terminology for this? This side you are having something like 2 hertz, and this side you are having 50 hertz because you want to feed it back. And the power here is SPG. That SPG you are eventually giving it to the grid. So this is called slip power. Please fill up the blank.
Recovery.
Great. Sleep power recovery scheme. Nobody is asking you to dissipate the power unnecessarily in the resistance. Okay. What is required here? Some power should get diverted out of the PG. SPG should get diverted to this circuit. That nobody says that circuit should have resistance. Generally, you please get rid of this resistance if possible. Okay. With the help of electronics, SPG, the amount SPG is diverted because we have decided the slip S. So by knowing what kind of slip you want, accordingly, some slip power is diverted, but don't dissipate it, don't waste it. So put this 2 converters, then whatever power is coming. So sometimes students say, no, this power will be very less. It is not very less. The reason is If you talk about one windmill, the typically windmill capacity is 10 megawatt. If you talk about a big campus, the power requirement is around 1 megawatt. Okay, so one windmill which is meant for 10 megawatt power can take care of such 10 such campuses. Whatever campus you are studying or you are working, that campus requirement may be power requirement may be 1 megawatt. So 10 such campus power requirement can be met by one windmill, 10 megawatt windmill. So this slip power is not going to be less, right? So that also we will see after some time. So it is a significant. So whatever we are investing on this small power electronic converter, small why I am saying compared to the power electronic converter which is meant for converting entire 10 megawatt, transferring entire 10, compared to that, this converter sizes will be small in size. The semiconductor devices have to carry lesser current related to that. So therefore, I'm saying small converter. So this slip power, if you are transferring to the grid, so then it will be, it will make the overall system as energy efficient actually, right? Now, what I have explained so far, induction motor, PG is equal to air gap power, which is mechanical power plus you can say SPG. Is that agreed? Basically, SPG means rotor copper loss. Yes. Now, this is for motor. I will write induction motor, right? All of you please listen carefully. And this rotor circuit, 3 windings are coming, terminals. So then you have this, I forgot to ask you, what is this called? This is called frequency converter. Okay, frequency converter comprises 2 power electronic converter. One converts AC to DC and another one is a DC to AC. So I will put this frequency converter. Then this will go to grid. All right. So PG is the air gap power, and this is the rotor, and this is the shaft. Suppose if the speed, earlier we started, no, asynchronous motor means the speed can be more than the speed of the magnetic field. Many of you had agreed. Okay. So that means what will be the slip that time? Hanji. Hello. Hello. Am I audible or not audible? Yeah. So tell me what I was asking. The speed could either be less than I have explained. Suppose if you assume that speed is greater than ns, speed of the rotor is greater than the speed of the magnetic field. Assume right now you assume. Rachana, you are not agreeing to this, correct? No, but you assume.
Yes, sir. Okay.
Yeah, for the time being you assume. If n is greater than ns, what will happen? What will be the slip? Tell me no.
Negative slip, sir.
Great, negative. Okay. Now you tell me what is the change here. PG is equal to PM minus SPG. Okay. Let's talk about per unit. let's say PG is 1. What is the contribution of PM and SPG? Can anybody guess? Take PG as 1. What is the value of PM? Somewhere around 0.8, because it's a motor. So we want most of the electrical power, most of it should be converted into mechanical power. So even if you say 85%, no. So let's have some round number, 0.8. So then 0.2 will be some losses. Out of that, let's say 0.1 is the rotor copper loss. Or the power that is extracted. From now onwards, we cannot say rotor copper loss. So it is a power, either you say slip power or it is a power extracted from the rotor circuit. Is that clear?
Yes,
It is
sir.
a power. Great. It is a power extracted from the rotor circuit. Now, although it is not convincing to you at this moment, let's assume, suppose if the rotor is moving at a speed greater than the speed of the magnetic field, but still it does the motoring. Because you are giving electrical power from the stator side and the rotor is rotating. Okay, but at a speed greater than that. It will not rotate by itself because S is negative. So as per this expression, it is PM minus SPG. Now, can you say something how this is achievable? It may not happen by itself, but can you tell me, is it achievable? By some means. Hello? Is it achievable or not achievable?
It's achievable.
Great. How it is achievable? Okay, I will give you one hint. Some power flows from rotor to the converters and then grid. That is SPG. Now we want minus SPG. It's not hint, actually it is telling the answer, but even then I am expecting you to respond to this. What happened? Many people are keeping quiet. I think it's boring. Anna? Manigandan?
Sir, not like that, sir. Actually, we are just listening to you, sir. It's a very interesting session, so that's why we are just listening your words.
Oh, okay, you are pleasing me. Okay, so generally I used to tell the participants in other programs, you will have to take care of me today. I will take care of you. Win-win situation. So you are nicely pleasing me. I am pleased. But even then, no, it will be good if we talk actually. Right? Nobody is going to mistake if the answer is incorrect. See, I will tell correct answer because I have prepared. Right? So don't think that you speak so that no, it is comfortable. That's all, and nobody will mistake here. SPG, I have given an arrow mark now, but now there is a requirement of minus SPG. Minus SPG in what case? Where n is greater than ns. Plus SPG is for a case where n is less than ns. Okay. Now I've given almost I've told everything. Only thing is you will have to say.
Induced EMF, sir.
No, you listen. From the rotor, you are taking SPG and going through the converter and then feeding it to the grid. So that is for the case n less than ns. Now, how do I achieve n greater than ns? For this question, Rachana will not answer, I know, because she is very much convinced that this is not possible at all. Anna Rachana?
No, sir.
Dekho, you assume that it is possible. Can you logically think? There is no subject here. SPG,
Is it possible,
n
sir?
less than,
Actually,
yeah, it is possible, but only thing is how it is possible. That is what I'm asking. So SPG goes like this. Now I have an expression here, I have a term here, minus SPG. How do I achieve this? Basically, power invariance we are.
sir, actually, I'm not sure, but I will tell you how it will be. Suppose,
Yes, yes.
let's assume, sir, how it will be. Actually, synchronous generator and synchronous motor is the same principle, sir. Suppose if there is no, okay, there is no power, let's say the flow of direction, the electricity flow of direction will be reversed. So that case,
Great.
the speed, sorry, sir.
Great, man. So basically, you are saying like this, right? Correct?
Yes, sir. You're right.
Correct. Okay. So SPG means you will extract the power from the rotor circuit. Okay. Now, in the second case, we have N greater than NS, for which we are having the slip power is minus SPG. So negative sign indicates the power is flowing in the opposite direction. What it means is it will not flow by itself. It has to be dash. Can you put an appropriate word here? Now, English class. Can you put controlled? No, power is controlled. No, see, I'll repeat. If for the speed less than synchronous speed, you have to extract the power from the rotor circuit. Extract. Now, for the speed to be greater than the synchronous speed, you have to dash power to the rotor circuit. Can you put an appropriate word?
Reduce.
Introduce. Okay. Inject. So inject is appearing to be better.
Yeah, correct.
Yes. Yes. So you have to inject the power in the rotor circuit. Okay. So inject the power in the rotor circuit means, so this is the converter. Let's say this is the converter 1, this is the converter 2. Okay. So this operation is called subsynchronous. So what is this operation called? How is my
Super synchronous.
super synchronous? Okay. Hey, how is my handwriting? Hello, how is my handwriting?
Very neat.
Very neat, huh? Okay. Who is this? Shyam.
Nice.
Yes.
Nice only, sir, not neat.
Hello. Wait. Nice. Which is superior here? Nice or neat? I'm confused now.
Nice means the way of representation is nice, sir. The handwriting which you are asking is maybe using of pencil, it will be not neat. I think maybe if you use pen, it will be good. I think so, or some markers, it will be good. It's my suggestion, sir. Don't mistake me. Sorry,
Manikandan, you are a faculty member or a student?
sir. Actually, I'm a designer, sir. Solar designer.
What? Designer?
Hmm.
Okay. Oh, from industry. You have come from industry. Okay.
Yes, sir. Yes.
Yeah. Okay, I have to improve my handwriting. I will try later. Okay? I'll improve my handwriting. So this is called supersynchronous, subsynchronous, supersynchronous. Okay. Now for subsynchronous mode, the converter 1 is acting as dash. Please fill up the blank. For the subsynchronous mode, converter 1 is acting as dash. Okay, I will tell rectifier. All right, rectifier. Suppose if the slip frequency is 2 Hertz, so it converts 2 Hertz to DC. Okay, what does the converter do? Converts DC to 50 Hertz AC. So the converter 2 acts as inverter. Right. Now for super synchronous mode, you please tell me. you have to inject slip power to the rotor circuit. So tell me, converter 2 acts as?
Inverter.
Converter 2 acts as. I asked 2. 2. Converter 2 acts as?
Rectifier.
Great. Rectifier. And converter 1 acts as inverter. Okay.
Inverter.
Now, yes, great. Out of these two control, you please see carefully and then tell me which control is difficult. Okay. Before proceeding further, whether everybody is convinced now that induction motor can rotate either at a speed less than the speed of the magnetic field or at a speed greater than the speed of the magnetic field. Now, how many of you do object? Hello, Rachana?
Sir, in case of when we operate the machine above synchronous speed, the torque produced is generally like electromagnetic torque produced is opposite to the mechanical torque. So, uh,
Wait,
so
wait,
how?
wait, wait, wait. Wait. We are talking about motor only. Generator,
Yes.
after this only, I will come to generator. We are
Okay.
talking about motor. Now, with this explanation, are you convinced induction motor, if it is a design for 4-pole 50 hertz supply, the magnetic field is going at 1500 RPM, but it can rotate at 1450 RPM. It can rotate at 1520 RPM also, as long as you are doing this control. Is this convincing or not convincing?
It is
Convincing, sir.
convincing, sir.
Great. So whatever is written in the book, induction motor rotates at a speed less than the speed of the magnetic field is applicable only for squirrel cage induction machine. But if you are having a phase bound induction machine where you have two windings, and if you are willing to make use of power electronic converter and implement the control, then it can rotate at any speed other than the speed of the magnetic field. Okay, so that is why it is known as asynchronous motor. So all the time, if you take the word asynchronous motor, that terminology, then you will be very sure. Nobody will do any mistake. Okay, it is not the inability of the machine that it cannot generate mechanical power at a speed greater than the speed of the magnetic field, because you are giving electrical supply to the stator and you want it to operate at a speed greater than the speed of the magnetic field. For that, you will have to inject the slip power. So basically what you are doing, this one is whatever I'm going to draw. This is not in the book. You will have to tell me if I'm wrong. Okay, so this is the synchronous speed, and now I want you to sketch the characteristic corresponding to a point. So this is the operating point. Now I want to go to this point. Okay, so this is a super synchronous mode, and this is a subsynchronous mode. This point, subsynchronous mode, is there in all books. Okay, now I want to go to this point. How do I go? So what will be the characteristic? So what I am saying, the characteristic will be like this. Okay, so if this is the characteristic, so this is for motor, torque, speed, and this is for generator. I'm not interested in the remaining part of the characteristics because the operating point is somewhere here. Okay, so there is no need to draw this characteristic. It's of no use. Okay, and this characteristic is for super synchronous mode in case of motor. So this is also actually motor. So whereas these two are for generator, which I will come to that later. Whether this one is acceptable to you, this is not there in the book. Okay, that doesn't mean I'm going to make a patent on this, but I'm convinced that if you can operate here, so that time the sleep is here, so you will extract SPG, extract SPG from rotor. So as per Manikantan's suggestion, I will not use pen. Extract SPG from rotor, this side, whereas here inject SPG to rotor, right? So by itself, it cannot operate as a motor at a speed greater than the speed of the magnetic field. So similarly, even for below synchronous speed, by itself it cannot do, right? You have to use power electronic converter and you have to control that. Do you follow what I'm saying? Hello?
Yes, sir.
Even for subsynchronous mode, it will not do by itself. Why it will not do by itself? Because you have to convert this to rectify and this you have to convert to 50 Hz. If you are not ready to do, even subsynchronous mode is not possible, right? Similarly, you have to do the control. So if you want to control the operating point, speed control you want to do, you have to do the control, whatever may be the mode, subsynchronous mode or supersynchronous mode. Now, to convince you, I'm making this statement. You call it as a asynchronous machine so that no, it will be very clear. All right. I will sleep now. Hello? Okay, tell me. Out in subsynchronous mode or supersynchronous mode, from the control aspect, which is difficult out of these two controls, subsynchronous control, supersynchronous control, out of these, where you see difficulties more? The options could be like, no, in both way difficulty is there, equal level of difficulty, or in one there is slightly more difficulty because that control has to be done, otherwise the operation is not going to be proper. So which is your option?
Super synchronous will have more difficulty, I think.
Second one, sir.
Yeah, okay. Super synchronous control is difficult. So can you explain that why?
Because it injects, injects power to the supply.
Inject power to rotor circuit, not supply. Inject power to rotor circuit. Now, which part is difficult? There are two converters. Where you are seeing difficulty? Your answer is correct. Super synchronous mode, it is slightly difficult control, and it should be properly done. Otherwise, you will not be able to operate the motor at that particular speed. You have decided to be away from above synchronous speed, and that speed you have already decided. Super synchronous is difficult. But can you tell me, there are two converters, where you are seeing the difficulty?
DC to AC, sir. DC to AC, sir.
DC to AC converter 1, correct?
Yes, sir.
Great. Who is that? Manikantan. Okay. Yeah. So here it is a DC side, and here because here we don't know whether the frequency has to be 2 Hz, 2.5 Hz, 3 Hz. We don't know. It has to be matched. Why? Because you want somewhere here. So that means you will get. So after some time you may try to want this, because this point is decided by the load that you are going to connect. Right now, you may say, no, this is the point. This is the point. This point is decided. I don't know the load characteristics. Load characteristics could be like this. Okay. So load characteristics, if it is like this, it is demanding varying power. So this one is a motor characteristics. This is the load characteristics. the point of intersection between the motor characteristics and load characteristics is going to be the operating point. If the load is changing, then motor is supposed to supply whatever load demands. So it's not, we can't simply say, no, we have decided this much slip, so we will inject this much power. No, that slip will be decided in consultation with the load, what load demands. So every time, no, we will have to take care of the control. So if I talk about subsynchronous, okay, subsynchronous, just I will explain, although you have responded that supersynchronous is difficult, but just for clarity for everyone, I'm saying, if it is a subsynchronous mode, whatever power you have to extract from the rotor circuit, so let's say whatever may be the frequency, 1.5 hertz, 2 hertz, 3 hertz, you will convert into DC. Okay, there is no control at all. Actually, AC is converted to DC, so you need not worry. And since you are connecting these lines to the grid frequency is always fixed 50 hertz, so DC to 50. So whatever PWM based converter you have, so that will be operated such a way it will convert DC to AC 50 hertz. So 50 is fixed, and you need not worry whether this is changing or not changing. AC to converted to DC. So there is no difficulty at all. Whereas you want to inject power. When you are injecting, injecting power, you can also say that synchronizing power. So from the grid, you are taking some power, a part of power, it has to be injected with the grid. You cannot randomly inject because there is already a three-phase supply, and the three-phase supply is at very low frequency, 2 hertz. Right. So now you will get 3 phase here. So this voltage has to be matched with this voltage. This phase sequence has to be matched with this, and whatever frequency you will get. So this DC 2 hertz. So that frequency has to match with what is the frequency of this rotor side supply. Is that understood? Okay. So.
Yes, sir.
Okay, clear. Okay, so the converter one, there is a challenge in super synchronous mode. That's all. Okay. Now we will go to generator. Okay, it must be easy now. Mechanical power comes, and you have the rotor circuit, and again converter. So this stator, stator can be connected to the grid, right? So one more circle I'll put. The stator is connected to the grid. Let's say it's 50 hertz supply. So grid is connected. So grid is connected. Therefore, there is a traveling magnetic field, okay, which goes at speed ns 120 f by p. Now here the rotor is rotated at a speed n. For the same machine in the motoring mode, n can be greater than ns, n can be less than ns. Okay, this is for motoring mode. Okay, now we have basically I want to connect to the grid eventually, right? So before connecting to the grid, you will have to put a transformer. The transformer I have skipped everywhere. Now tell me the power balance equation. You are comfortable with which mode? which mode? Super synchronous mode. We are talking about generator now. Okay. So motoring mode I have written earlier. Now we are talking about generating mode. So you are immediately comfortable with which mode? Generator means which mode? Whatever is written in all books. N greater than ns. Correct? Hello.
Yes, sir.
Okay. Now for this, can you tell me the power balance equation? PM is equal to
Input power minus the rotor copper loss.
can I say like this? PG plus SPG.
Yes.
Okay. N less than ns. So whatever mechanical power. So PG now actually everything is getting changed. Okay, the direction it will flow from the stator to the grid, something like that. So minus SPG, right? So convention we will change. Okay, so when the speed of the rotor is greater than the speed of the magnetic field, rotor circuit also will provide power to the stator. Okay, when the speed of the rotor is less than the speed of the magnetic field, still you want to generate. Okay, because the speed change is from 1510 rpm to 1490 rpm. Still you want to generate. In that case, you have to inject power to the rotor circuit. So this is SPG, and this is for N greater than NS, and this is for N less than NS. Any question here? Any question? Shyamji? Hello? Shall I proceed?
Yes, sir. You can continue, sir.
Okay. Is there any question up to then, or up to now? So the conclusion is this induction machine can function as a generator or a motor at any speed other than the synchronous speed of the magnetic field. To achieve this, you have to go for a control. That's all. So the answer for this rotor speed can either be, it should not be equal to synchronous speed. That's the answer. Actually, that option is not given. Okay, this is just to misguide people. Now, if you talk about there are 4 schemes. Now you will have to tell what scheme is the better scheme. First one is squirrel cage induction machine as a generator. So you don't have any access to the rotor. The stator is directly connected to the grid, directly in the sense via transformer. So basically the traveling magnetic field is taken care by the grid. Then the active power is transferred to the grid. But the operating point is very limited, because if you want the induction machine to be efficient, the sleep should be very low value. If the sleep is more, it is not going to be an efficient operation. Why it is not an efficient operation? Yes. Virendra ji, you want to say something? Virendra ji, you want to say something? Okay. So for efficient operation, the sleep has to be low. So when you say the sleep is low, that means what? It's a narrow speed range operation. That's why it's called as a fixed speed. Fixed speed means narrow speed, something like that. All right. Now you have another case, once again, squirrel cage induction machine. Now, can you tell me the difference between the first and second, but it is referred as a variable speed. Okay. Can you tell me the difference between these two? Can you tell me the difference between the scheme 1 and scheme 2? Whether you are all thinking, or should I tell the answer? And scheme, tell me.
Yes, sir. Sir, actually, the fixed speed squirrel cage induction motor, it is directly the constant power, sir. It is directly to the transformer, and we are giving to the grid. As we see, like a previous study which you explained to us, in the second one, variable speed squirrel cage, you can adjust variable the speed of the rotor, and also that there is stage one control will be there, and stage two also be there in the second one. So this is the difference between the both of us.
Okay, great. But we have moved from motor to generator. Okay, so basically, what I'm trying to say is, since you have connected the grid to the stator windings of the machine, the traveling magnetic field will be the traveling magnetic field. The traveling magnetic field will be there at that speed. Now the speed of the rotor should be very close to the traveling magnetic field speed in the first case.
Yes, sir.
Whereas in
Yes.
the second case, there is a kind of a isolation between the grid and the machine, because this frequency converter. So whatever may be the speed, even if the speed is very less, like we have designed, let's say we have designed for 1500 rpm as a synchronous speed. Now the speed is just 500 rpm. That's fine. So 500 rpm also you can connect. The reason is the frequency of the output that you will get out of the machine now maybe 10 hertz, 20 hertz, because it's connected with the wind speed. And we have whatever gearbox we have, with that we are getting, let's say, very low speed, 20 hertz only we are getting. That doesn't matter. That 20 hertz can still be connected to the 50 hertz with the help of this frequency converter, right? So therefore the speed of the rotor in the second case, we need not worry. It is low, or it is closer to the 50 hertz traveling magnetic field speed. We need not worry about it, because these two systems, these two different frequency systems are isolated, and they are coupled through frequency converter. Whether that part is clear to everyone?
Yes, clear, sir. Clear.
Yes, sir. Clear.
Fine. So that is why it is called variable speed operation, and it is the in the characteristics. If you want to sketch, maybe I will have to draw that. If I have to sketch the scheme 1, so there is a single frequency, okay, because it is directly connected to the grid. Whereas the scheme 2, you can have many such lines. So the operating point, the turbine speed, can be anywhere here. Do you follow what I'm saying? So this is just for 1, whereas this entire range is for 2. Is it understood?
Yes, sir.
Okay, okay. Now we can go to the third scheme, right? Third scheme, you have to provide field in the rotor winding, whatever field winding you have, and stator will give the power. Once again, this is also called variable speed. Whenever you put the frequency converter, that's called variable speed. Is that okay? So the third one is easy. Now the fourth one, you come to fourth one. The stator is directly connected to the grid via transformer, and the rotor side you are connecting frequency converter. Now it's very silly to ask this question, but even then I'm asking just to see whether it is clear. Whatever, why we are connecting frequency converter in the rotor side? Why we are connecting frequency converter to the rotor side? Hello. We have already discussed at length.
Sir, as we talk about the synchronous speed, sir, we discuss about the variable speed and all, so we have to control the rotor only, sir, not in the stator part. Stator is the separate. We have to control only in the rotor side.
No. Why we are connecting frequency converter? I think you are telling, but I'm looking for some accuracy there. Why we are connecting frequency converter in the rotor side?
So we can go above the synchronous speed also by connecting.
Yeah. So basically, we want to play with the slip power. Either we want to extract the slip power in one case, in another case we want to inject. Okay.
Inject.
Yeah. In which case you want to extract the slip power? You tell me directly, subsynchronous mode or supersynchronous mode. This is for generator. In which case you want to extract power from rotor? In which case you want to extract power from rotor?
So, sir,
Super synchronous, great. And in the subsynchronous mode of operation, you will inject power to the rotor circuit. Now, I want you to compare the size of the power electronic converter in scheme 2 and 3. Size of the power electronic converter, whatever you have in the stator in 2 and 3. Please compare this size in the sense that rating of the switches that you use, power capability. So that one, can you tell me? Because the turbine is designed, let's say 10 megawatt. So the 10 megawatt gets converted into power close to 10 MVA. So that 10 MVA you want to feed it to the grid. So that much power has to flow through the semiconductor devices. You have 6 devices in the converter 1 and 6 devices in the converter 2. Okay. Similarly, the same story holds good for the scheme 3 also. Now compare this size. Options could be they are of similar value, similar rating. These converters are have to handle different similar power level or different power level. Please choose. Anji. No, this is not difficult question. You tell me. Scheme 2 and 3.
Sir, I can answer, but I am not sure I am right. Sir, actually, in the scheme 3, we are having a synchronous generator. Synchronous generator, we can play with the slip by using the converters.
No. Slip is not applicable for synchronous machines. Slip, the terminology itself
Sorry.
is applicable only for induction machine.
Induction, yes, sir. Sorry. For induction motors, you can play with the slip, sir. For synchronous motor, you can play with the synchronous speed.
Yeah. See, my question is power level. I said 10 megawatt turbine, then 10 MVA generator. So 10 MVA power has to go. Similarly here, now basically, what is the power handling? What is the power that is handled by this power electronic converter that you have connected to the stator of the scheme
Yes.
2 and scheme
Okay.
3?
Clear.
Similar power
Clear.
level, different power.
Yes,
So,
sir.
sir,
Actually, in this,
second,
see,
No. I am giving you only two options: similar power level, different power level. You have to choose one of these. That's all.
different, sir.
different power
Why?
levels.
Why different power level? Why different power level? So here also you are extracting the power. It's a generator and you are feeding it to the grid. Here also the power is generated. It's a synchronous machine, right? So because the rotor circuit, you are just all the time you will be giving a DC current here because you are establishing the electromagnet here. So the main power is coming only from the stator. So why you think it is a different power level? Is it because that my diagram I have not shown properly? Some changes there that
No,
boxes.
sir. Actually, sir, synchronous generator from stator to directly we are feeding to the transformer. Let's say it is a 10 MVA. This is easy for you to extract the power from DC to AC with a single converter. Suppose if you are going for the rotor, the AC to DC and the converter 1 and converter 2, it needs the minimal power to control the rotor, sir.
Nee. The scheme 4, I'm not asking. I am talking about scheme 2 and 3. Then I will go to scheme 4. Scheme 4 is a separate question. I will come to that. Now my
In 3
question
only,
is
sir.
scheme 2 and 3, the power converters that you have connected to the stator, whether they have to handle similar power level or different power level. First option is similar, second option is different. See, the rotor converter is always giving the current to the electromagnet. So because you want a field to be established here in synchronous machine, so you are connecting this. So this rotor converter is not going to feed any power to the grid. It is always taking the power from the grid because it has to establish the magnetic field. Now my question is, the stator converter, the converters that you have connected in the stator side in scheme 2 and 3, whether they will handle similar power level or different power level, because the turbine, both the turbines are same.
So I think it's similar, but in case of induction generators, then how
Madam,
the
madam, induction generator, which generator? Scheme 2 or scheme 4?
a scheme too, sir.
Scheme 2, what is your question?
Then, sir, about that excitation energy that we have to.
Excitation, it will come. So when I put this power electronic converter, maybe I will have to draw that actually. So this is the stator. Now what you are getting, you will do the control here. Q comes this way and P goes this way. Do you follow what I'm saying?
Yes, sir.
Yeah. So basically you will be playing, suppose if okay, maybe I did not explain one thing. If I have the voltage waveform like this, so then current waveform like this. Okay. So let's say this corresponds to P plus JQ. Okay. Some convention. Okay. Some active power and reactive power. So if I make the current waveform like this. So this is case 1 and this is case 2. Case 2 corresponds to P minus JQ. Is that okay? Hanji?
Yes, sir.
Okay, so basically you can reverse both P and Q by playing with the voltage and current waveform. and this manipulation of shifting the phase of this current waveform in line with the voltage waveform, that is always possible with the semiconductor devices. Only thing is there is some requirement need to be met. If you want to do the reverse power flow, if you want to achieve, there has to be active sources both sides. So then only the reverse power flow is possible. Whereas the reactive power, you can do even without there is a power source. It is possible to do by suitably adjusting this by doing with the pulse width modulation. All right. So when I say there is a converter and that converter is giving the power to the grid, don't think that there is only one side of active power is taken from the generator and it goes to the grid. But for getting that active power, you require magnetic field. That magnetic field is coming from it's established, not coming from, it is established by the grid supply, for which you will have to do the appropriate control on this converters. Okay, so the pulse width modulation on the semiconductor devices is to be done properly so that the current waveform is shifted. So something like current waveform will be shifted. So not I2, maybe some other waveform like this. So the current waveform gets shifted. Therefore, you will have the P minus JQ. Okay, so and if you reverse it, so then it becomes minus P, which case that case we don't want actually. Do you follow what I'm saying?
Yes, sir.
By placing the current waveform in with voltage waveform, by adjusting the phase angle of the current waveform with voltage waveform, it is possible to do that. Okay, now you please tell me the last scheme. With that I will stop. Last scheme. Comment on the power electronic converter used in the rotor side in the last scheme. There is no power electronic converter for the stator side. It is directly connected with the grid, and you are putting converters in the rotor side. You want to play with the slip power. Okay. Now compare the size of same 10 megawatt turbine. What is the power handling capacity of the converters in the scheme 4?
That is very less compared to the scheme.
Great. That is very less because sleep power is very less. So that is why this doubly fed induction machine is widely used in wind energy conversion system. Okay. So this is widely used. So with this, I am stopping here. Is there any question?
I request participants, please ask if you have any query, please ask. All participants, please listen. If you have any query, please ask.
Okay, I think there are no questions. If there are any questions, you can approach me later also. So thanks for your patience.
Okay, thank you, sir. Thank you for this wonderful session. At the end of this program, I would like to convey the thanks from the College of Engineering and Technology, Pambori Jalgaon, to Dr. Ragavan sir for sharing his valuable knowledge and valuable time with us. Thank you so much, sir. There is one important instruction to all the participants. Next session will start sharply at 2:30 p.m.
2:15.
2:30 p.m. Please join on time. Thank you.
Sir, one request, Raghavan sir. So please send your PPTs. So